and she talked about Hölder continuity of the Lyapunov exponent for Markov's cocycles.
Okay, so thank you, Carlos. Good afternoon, everyone. So first, I would like to thank the organizers for the great conference. I have been learning a lot during these weeks in Poland, and it's a great opportunity to be here. So thank you very much. So today I will talk about a joint work with Ao Cai, Marcelo Durães, and Silvius Klein, and it's about the regularity of the Lyapunov exponents in the context of Markov cocycles. So before to recall the definition of Lyapunov exponents and the definition of Markov cocycles, I would like to start with the definition of linear cocycles. So let's start with this. Consider X me T, an ergodic system. A linear cocycle is a skew product map F such that the base dynamic is given by the iterate of X by T, and the fiber is given by a measurable map A with values in the space of M by M invertible matrix. Okay, so here I'm fixing the dynamic T. So sometimes we can denote the linear cocycle FA just as A, okay? Okay, so we can iterate the linear cocycle, and the iterates are given by the following. The base is given by the nth iterate of X by T, and the fiber is given by the product of the matrices A along of the orbit of X. Okay, and we know that if we have a linear cocycle F, we know that by Kingman's ergodic theorem that the sequence 1 over n log of the norm of this product of matrices converges to a number L1, me almost Fx. And this number is, we call this number as the first Lyapunov exponent of A. Okay, so we can define similarly the other Lyapunov exponents, L2 until Lm, change the norm of the fiber iterates n of x by the other singular values. So we have the following. We have cocycle A. Remember that I'm fixing the dynamic T, okay? So sometimes we cannot fix the dynamics and we have differentiable cocycles, but here I'm just fixing dynamical T. And it's natural to ask about the regularity of this map. So are Lyapunov exponents continuous functions on the data? Well, in general, the answer is no, but it's possible to prove the continuity of the Lyapunov exponents for some classes of linear cocycles. Okay, so I would like to talk about some of them. The first one is the quasiperiodic cocycles, and a quasiperiodic cocycle is a linear cocycle over the torus translation. Okay, and in this context, we have some results about, but I would like just to mention two of them. The first one I would like to mention is from Avila, Jutomiskaya, and Sadel. And they prove in this context, they prove the continuity of Lyapunov exponents, but in the context where the D here is equal to 1, so for one-dimensional torus. And, well, okay, I have some notes because maybe I didn't, I'm sorry. Okay, but they prove this for D equals 1. Okay, and just remember, okay, for quasi-periodic linear cocycles. But here in Avila, Jutomiskaya, and Sadel, they didn't obtain their models of continuity, okay? And in this case of Duarte and Klein, obtained their models of continuity in the case of D is equal just D, so for D-dimensional torus, and when alpha, the frequency alpha is just is a generic condition, okay? And okay, so they prove the continuity. They prove that the Lyapunov exponents are locally Hölder continuous. Okay, I like to mention that in this first case here, they prove it for this A and alpha. So the first Lyapunov exponents are continuous with respect to the cocycle A and the frequency alpha. Okay, so the next result that I'd like to talk is about the random cocycles. And a random cocycle is a linear cocycle over a Bernoulli shift. And here the fiber is given by a measurable map A that depends only on the first coordinate of omega. Okay, so here it's local constant. And for this, we have some results. The first one, I'll just like to talk about 4 of them. The first one is the Furstenberg-Kiefer, and they prove for a generic random linear cocycle that Lyapunov exponents are a continuous map. And Lepage proves that for an irreducible random linear cocycle, and if you have the gap between the first Lyapunov exponents and the second one, then the Lyapunov exponent is locally Hölder continuous. Peres proves a result when M is finite, okay? And he proves that if the first Lyapunov exponent is simple, then the map is analytically with respect to the probability vectors. Okay, and Bocca-Viana proves continuity in the case of random cocycles, but in the case with dimension 2. So this M here is equal to. Okay, so my case in our work, we like to understand the regularity of Lyapunov exponents, but in the context of Markov cocycles. Okay, and okay, so I have to introduce the concept of Markov cocycles. But first, try to understand that Markov cocycle is a generalization of a linear cocycle over a Markov shift of finite type. Okay, try to understand like this. So there is some definitions that I would like to talk about, and we can think about this definition as a generalization in the other case. Okay, so for example, the definition of Markov kernel. So consider M a compact map space and B its Borel sigma algebra. Okay, a Markov kernel on M is a continuous map K that goes from M to the space of probability measure on M. In other words, what this means? This means the following, that if I have X, a value on M, then Kx is a probability measure on M. So if we take a measurable set E, Kx of E is the probability of X goes to the set E. Okay, so we can iterate the Markov kernel K. So the first iterate is just K. And the n iterate, or that is the Knx of E, is the integral of the previous one with respect to the measure Kx. So in other words, this means the following. Knx of E is just the probability of X goes to E at n iterates. Okay? Okay, so if I have a Markov, something that I like to say about, to continue. I told you that we can think about the generalization of a Markov shift of finite type. So this Markov kernel here is like the generalization of a stochastic matrix. Okay. Okay, so go on. If I have a Markov kernel, I can associate a Markov operator. So the Markov operator is a linear operator Q that is from the continuous map M to itself, and Q of F of X is the integral of f with respect to the measure kx. Okay. So another definition that we have to, when we need, is the stationarity of a measure. So a probability measure nu is called k stationary if nu is kx invariant with on average with respect to nu. Okay, and this is the generalization of a stationary measure in the other context, in the context of Markov shift of finite type. And the Markov system is a trip mk nu, where M is a compact metric space, K is a Markov kernel on M, and N is a stationary probability measure with respect to the Markov kernel K. Okay, so now we can talk about Markov cocycles. And a Markov cocycle is a linear cocycle over a dynamic. This dynamic, what is this dynamic? Markov shift. So for do this, consider a sigma k mu, a Markov system. That is, sigma is a compact metric space, k is a Markov kernel, and mu is k stationary probability measure on sigma. And consider this space of sequence with Simons on sigma. Okay, and p mu, the Markov measure on x. Well, this means that p mu is a generalization of the Markov measure on the context of Markov shift of finite type. So this means that p mu here is a measure on x with initial distribution mu and transition kernel k. So p mu has a relation with this k here. So we can consider now the shift map. And the system x, p mu, sigma is ergodic, and it's called Markov shift. And now we can now talk about the Markov cocycle. So Markov cocycle is a linear cocycle such that the base is given by the Markov shift and the fiber is given by a measurable map A with values in the space of M by M invertible matrices, and A here depends only on the two symbols of sigma. That means that A here depends only on the first two coordinates of omega. Okay. So I would like to understand the regularity of the Lyapunov exponents in this context. We have some results about this. I would like just to mention three of them that it's related with our work, okay? So the first one is from Paris. And Paris proves that it's in the same work that I told you before. Paris proves that when sigma is finite and the first Lyapunov exponent is simple, then the Lyapunov exponents depend analytically of the probability transition, okay? The second result is from Melo Viana, and they prove that for Markov cocycles of dimension 2, the Lyapunov exponents are continuous functions on the data. But here, they didn't obtain a modulus of continuity. And Duarte and Klein obtained a modulus of continuity in the following way. So, for mixing Markov cocycles, that satisfies an reducibility hypothesis, and the first Lyapunov exponents is simple, then the map A goes to L1 of A is locally Hölder continuous. Okay. Okay, but in our work, we like to understand this. So, okay. So we like to understand not just varying the cocycle, but the Markov kernel too. Okay, so we like to understand the regularity of this map. Okay, so for do this, I would like to obtain a modulus of continuity of this map here. So to do this, I have to ask some hypotheses. Okay, And I have to ask some hypotheses on the fiber and on the base. Okay. So for the fiber, we will ask something that it's about irreducibility. So a measurable section V is called invariant when it follows we have the following. So V of omega n minus 1 is a linear subspace of Rn. So something like this. Okay. So this is V, and then we call that this section is is invariant if A of omega n minus 1, omega n minus 1. If I apply this to our section, then this is just V of omega n for me almost for P me almost F omega. Okay. And we say that a Markov cocycle is reducible with respect to the Markov system K-mu if there exists no measurable proper invariant section. Okay. So this is the first hypothesis that we ask. We ask this in the fiber, but we have to ask a hypothesis too. We have to give a hypothesis too about the basis. And we ask something that's about uniformly ergodic. And we consider sigma K-mu via Markov system. And we say that a kernel K is uniformly ergodic if K and omega 0 converge to mu uniformly on omega 0 with respect to the total variation norm. And we can think this as a generalization, again, as a generalization of Markov shift of finite type. And this is just the, we say that the stochastic matrix is aperiodic, okay? But here in a general context. Okay, so now we can talk about the result of our work. And now I'm just fixing that A is a Lipschitz Markov linear cocycle, and K is a Lipschitz uniformly ergodic Markov kernel. Okay, so from now on, I will just consider this. If not, I will see. But I think it's not necessary. Okay. So suppose that the first Lyapunov exponent is simple. That is, the first Lyapunov exponent is greater than the second one. And suppose that the cocycle is reducible. Then the Lyapunov exponent is locally Hölder continuous with respect to the A, to the cocycle A, and the Markov kernel K. Okay, so I have to say something about this. Before to give the ideas of the proof. The first one is locally Hölder continuous. So for the locally Hölder continuous, I have to drink. Okay, for locally Hölder continuous, we have to talk about the space of linear cocycles that we are considering, okay? And we have to, so I will do this later. I will give the definition of the linear cocycle, the space of linear cocycle that we are considering, and the distance in this space too. The other thing that we have to talk, that I'd like to say, is about the irreducibility of the cocycle. Okay, so we can prove for a weak version of irreducibility too, but I just like to mention of this. The third thing that I'd like to say is about the cocycle. Here I'm saying that sigma is sigma times sigma, that A depends only on two symbols of sigma. But we can extend this result for any Lipschitz Markov linear cocycle that depends on a fixed finite number of symbols on sigma. Okay. And another thing that I'd like to mention is about what about the other Lyapunov exponents? Well, if we consider that the exterior powers of the cocycle are irreducible too, then the other Lyapunov exponents are locally Hölder continuous, as long as they are simple, okay? So, are there any questions? Okay, because oh, okay. So, the ingredients for the proof are the following. The first one is the Furstenberg's formula. So, the Furstenberg's formula characterizes the first Lyapunov exponent, okay, as the integral of some observable with respect to the stationary measure. So, with respect to the stationary measure. So we have to talk about the regularity of stationary measures. And the third ingredient that we use is the spectral properties of Markov operator associated to the cocycle. Okay, but Markov operator, but the previous one or not? So I would like to say something about this Markov operator that we use. So if you have omega n, the sequence, we have the following. Omega 0 goes to omega 1, that goes to omega 2, and go on, okay? And this goes with some transition that's given by the Markov kernel K. Okay, so we have our Markov cocycle. That is the following. So we know that it's the base is given by Markov shift, and the fiber is given by a omega 1, omega 0, V. And it is on the space of sigma n times Rn. Okay, so we can define the projective space, PF. So projective cocycle. It's okay to okay, so this on sigma m times the projective space. And this is just what? This is the base dynamic here is given by Markov shift, but here we take the class of this vector here, okay? So this projective cocycle induce a Markov chain. And this on sigma times the projective space. Okay. Okay. I will try. So this is a Markov chain on sigma times the projective space. Okay, and this is following. Omega 1, omega 0, V goes to omega 2, omega 1, A of omega 1, omega 0, V. One more step to understand what is going on. So omega 3, omega 2, A of omega 2, omega 1, A of omega 1, omega 0, and V. Okay, and go on. So this is a Markov chain. And why this is induced by this projective cocycle? Because of this. Here we have the iterates of this cocycle. So look, this is the first iterate of the projective cocycle. And we have the other iterates. The other iterates appears here in the other part of the sequence. And we have the following too. We have the following, that this part here, you can note it that this part is well defined by the previous one. Yes, because here we have omega 1 and omega 0 and V. So it's well defined by this. So, and about this, what about this part here? So this part here, we can get by the Markov kernel K, our Markov kernel, in our initial Markov kernel K. Okay, so now we have we can construct K bar that is a new Markov kernel that has relation with this Markov kernel K, and they give the transition of this sequence here, of this Markov chain here. Okay, so the spectral properties that I'm talking about, this of the Markov operator, is from the Markov operator that is associated with this K bar here. So I will talk about the spectral properties of this Markov operator here. Okay. Okay, so let's talk about a little bit about the proof. The first part is about the Furstenberg's formula. And we know we have that if you have a Markov system K-mu, then if you consider the continuous observable C, that is defined by the following way: log of the norm of the fiber, the A, the cocycle A in V. Then we can define the continuous linear function alpha, that is the integral of the observable C with respect to the measure M, that is stationary with respect to Q bar. So this M is stationary with respect to this Markov kernel K bar here, okay? And if we take the maximum of these values of alpha, so we have the following. For every omega 0 V, we have that the limit of 1 of n log of the norm of these matrices, the product of these matrices is equal then beta. For almost every omega that starts with omega 0, okay? And in particular, we know that this is equal then the first Lyapunov exponent. So we can characterize the first Lyapunov exponents as the maximum of the values of this integral here, okay? With respect of all K bar stationary probability measures, okay? So I told you that I have to talk about the space that we are considering, the space of linear cocycles, the Markov cocycles that I'm considering in our work. So for do this, I have to define the Wasserstein distance, and just recall the definition of Wasserstein distance. And the Wasserstein distance is a probability. The Wasserstein distance is a probability on the space of probability measures on sigma. And the Kantorovich-Rubinstein theorem characterizes the Wasserstein distance as the following. Well, the distance between two probabilities on sigma is just the sup of every phi Lipschitz continuous with constant 1, and the difference between phi with respect to mu and the integral of phi with respect to mu and the integral of phi with respect to nu. Okay? And the space of Markov cocycles that we consider is this. C, so as I told you, we are fixing the dynamics in the base. So I can just consider the note AK as the space of the Markov cocycle, okay? So this space is the following. A is a Lipschitz continuous function, Markov linear cocycle, and K is Lipschitz continuous in the weak star topology. So in this set, we can define a metric as the following. The distance between two cocycles is just the maximum of the distance between AK, the cocycle A and B, the cocycle A and B, and the distance between the Markov kernel K and L. And the distance between A and B is just the sup of the difference of the norm of the difference between A and B, taking the sup with respect to omega 1 and omega 0. And the distance that we considering for of the kernels is the following. Well, we know that K omega 0 and L omega 0 is now a probability measure on sigma. So now we can consider the distance between of k omega 0 and L over omega 0 with respect to the Wasserstein distance. And then we take just the sup with respect to omega 0. So we have the distance between these two cocycles is just the maximum of these two distances here. Okay. Okay, so now we can define the Markov operator, and the Markov operator Q bar is the Markov operator that corresponding to this operator K bar here. And note that Q bar of C is the integral of PC with respect to the measure K omega 1. And note that this part here is given by the Markov chain here. So, okay, so it's related with this part here. So the Q bar, it's related with this, the Markov kernel K bar. And we can prove that if we consider the Lipschitz linear Markov cocycle and K Lipschitz Markov kernel, and if we assume that the first Lyapunov exponent is simple and the cocycle is irreducible, then we have the following, that the Q bar of n of psi goes to the integral of psi with respect to a stationary measure of m with respect to the cocycle, the Markov cocycle. This means, in other words, this means this, that Kn goes to, in some sense, goes to the stationary measure of the cocycle AK. Moreover, with this proposition, we can prove that there exists a unique stationary measure of the cocycle. So there's just one stationary measure. Okay. Okay. So this part here, we have AK. It's possible to prove that AK goes to K bar of n if this map is locally Hölder continuous. So the other part, so we can prove just one more thing about this part here, is that this is equivalent in the case of random cocycles. This is equivalent to say that the Markov operator is quasi compact and simple. Okay, in the random cocycles. Okay. Okay. One more thing is about the following: the regularity of the stationary measure. It's okay. Okay. So the regularity of the stationary measure, and we can prove that the map AK goes to MAK, the stationary measure with respect to the cocycle AK, is locally Hölder continuous. So if we assume that the first Lyapunov exponent is greater than the second one, and the cocycle is irreducible, then the two cocycles that are sufficiently close to the cocycle AK, we have the following. For every alpha Hölder continuous, we have the following, that the difference between the integral of f. So now we have the following here: the stationary measure m with respect to the cocycle BL, and the stationary measure m here that it with respect to the cocycle DP. Okay, and this map is locally Hölder continuous. Okay. Okay, so now we can talk about the Fürstenberg's formula. I've already told you that we have the uniqueness of the stationary measures. So the first Lyapunov exponents is the maximum of the values of the linear function alpha. Okay, but we have the uniqueness, so we can just write the first Lyapunov exponent as the integral of the observable that I told you before. And in this case, well, we can just talk that we have that the following, that AK goes to MAK locally Hölder continuous. So we have this, that this locally Hölder continuous. A is Lipschitz continuous, Markov linear cocycle, and we have this log here, but okay, we can think that, well, there are a lot of things to do, but we can think that the cocycle AK goes to L1 is a locally Hölder continuous map, okay? So one more thing that I would like to talk about is something about work that we are in progress, that we're thinking about with another linear cocycles, okay? And so what about the other one? So what about Markov quasiperiodic linear cocycles? And a Markov quasiperiodic linear cocycle is a cocycle over a Markov quasiperiodic dynamical system. And the Markov quasiperiodic dynamical system is the following. So if we have a frequency alpha, I'm fixing alpha here, and we have a Markov shift. The Markov quasiperiodic dynamical system is just the product of the Markov shift with the torus translation, okay? And we can now, if we have a measurable function A, we can define a Markov quasiperiodic linear cocycle. So this is a linear cocycle over this dynamic. And here the fiber is given by A that depends only on the first two coordinates of omega and theta, okay, theta. Okay, so if we iterate this, we can iterate this linear cocycle, and it's just the iterates of the n iterate of the Markov quasiperiodic dynamic. And here the fiber is just the product of A along of the other, okay? And so we know by Kim's ergodic theorem again that the existence of the first Lyapunov exponents and the sequence converges to the first Lyapunov exponents for p mu times m almost everywhere. And this m here is the Lebesgue measure. And okay, so we know this, and we like to understand the regularity of this map, the Lyapunov exponents in this context. And here, okay, so this is, we can thinking about if the first Lyapunov exponent is simple, and if we assume certain hypothesis of reducibility, then the map is locally Hölder continuous. The first Lyapunov exponent is locally Hölder continuous. And in this case, there's a little more, it's a little more difficult because here, as I told you before, this part here says the Markov operator in the random cocycle, that the Markov operator is quasi-compact and simple. So quasi-compact and simple, that means that the spectrum of the operator is contained in this case, is contained the following. So it's contained in one point in the disk, and with the union of another set, it's contained completely on the disk. Okay, so this part comprise, we have the contraction of this part, and we have a point. But in this case, in the Markov quasiperiodic cocycles, the Markov operator, it's not like this. So it's not just a point here, it's the entire unit disk. So we have this problem here. Okay, you have a little problem in this part. And you have to deal with this in a different way. There is a gap spectrum, but it's not usual that we are used to understand in the literature. So we have to deal with this in a different way. And we use some techniques. Well, this is a work in progress. We didn't finish yet, but I'm just talking just to mention this. But another thing that we like to mention is that outside Duarte and Klein, obtained a partial result in the case of mixed random quasiperiodic cycle. So instead of considering the Markov shift here, they consider the Bernoulli shift and the Toro's translation. Okay, so this is it. Thank you so much.
Thank you, Aline. Some comments or questions? Okay. If not, so let's thank Aline again.
Thank you.
And we see you tomorrow. Thank you.